final value theorem of Z transformation statement. If Z of f of n which is equal to capital F of Z, then limit n tends to infinite f of n which is equal to limit Z tends to 1 Z minus 1 into capital F of Z. We'll see the proof. We know that Z of f of n plus 1 which is equal to, from the definition of Z transformation, n is equal to 0 to infinite f of n plus 1 into Z power minus n. So that is equal to, so substituting the value of n, so when n is equal to 0, so 0 plus 1 f of 0 plus 1 f of 1 Z power minus 0 plus n is equal to 1, when n is equal to 0, so you will get f of 1 Z power minus 0. When n is equal to 1, f of 1 plus 1 f of 2, right, Z power minus 1 plus etc. etc. Right. Now multiply Z and divided by Z. So you will get f of 1 first term plus f of 2 Z power minus 1 second term plus f of 3 Z power minus 2 plus etc. etc. So taking that denominator Z to the numerator, so 1 f of 1 plus f of 2 into Z power minus 1 plus f of 3 Z power minus 2 plus etc. etc. Taking that Z power minus 1 inside the bracket, so you will get Z into f of 1 into Z power minus 1, then f of 2 into Z power minus 1 into Z power minus 1 Z power minus 2 plus f of 3 into Z power minus 1 into Z power minus 2, you will get Z power minus 3 plus etc. etc. So that is equal to Z into adding f of 0 and subtracting f of 0. See, first f of 0 added and the last, so f of 0 subtracted. So Z into f of 0 plus f of 1 Z power minus 1 f of 2 Z power minus 2 f of 3 Z power minus 3 plus etc. etc. minus f of 0. So Z into f of 0 plus f of 1 Z power minus 1 plus f of 2 Z power minus 2 plus etc. etc. This is one term. Then multiply that Z with the last f of 0. So you will get minus Z into f of 0. So therefore f of Z, f of n plus 1, Z of f of n plus 1 which is equal to Z of the first term, right? Z into f of Z, capital F of Z, minus the last term Z into f of 0. Since we know capital F of Z which is equal to summation n is equal to 0 to infinite f of n Z power n. So expansion is nothing but the above term, right? F of 0 plus f of 1 Z power minus 1 plus etc. etc. Right? Now f of n plus 1 which is equal to Z into capital F of Z minus Z into f of 0. Right? Now Z of f of n plus 1 minus f of Z which is equal to, subtracting minus f of Z both sides, a minus f of Z which is equal to Z of f of Z minus f of Z minus Z into f of 0. So Z of f of n plus 1 minus the Z of f of n which is equal to Z minus 1 into f of Z minus Z of f of 0, right? Because capital F of Z is nothing but Z of small f of n, right? So which is equal to Z of f of n plus 1 minus f of n, because Z transformation common, minus f of n is equal to Z minus 1, right? F of Z minus Z f of 0. By definition, Z of f of n which is equal to capital F of Z which is equal to summation n is equal to 0 to infinite f of n Z power minus n. Therefore, summation n is equal to 0 to infinite f of n plus 1 minus f of n Z power minus n, because instead of small f of n you are having Z of f of n plus 1 minus f of n. So we are using Z transformation formula, right, which is equal to Z minus 1 f of Z minus Z of f of 0. So Z minus 1 f of Z minus Z of f of 0 equal to summation n is equal to 0 to infinite f of n plus 1 minus f of n Z power minus n, right? Taking limit Z tends to 1 on both sides, you will get limit z tends to 1, z minus 1 into f of z minus z f of 0 is equal to limit z tends to 1, summation n is equal to 0 to infinite f of n plus 1 minus f of n to z power minus n. That is limit z tends to 1 f z minus 1 f of z minus, as z tends to 1, z into f of 0 become f of 0, right? Because replace z by 1 into f of 0, so you will get f of 0 is equal to summation n is equal to 0 to infinite f of n plus 1, right, minus f of n, replacing z by z by 1, right? Limit z tends to 1, so 1 power minus n, so you will get 1. So that is why it is equal to summation n is equal to 0 to infinite f of n plus 1 minus f of n is equal to limit n tends to infinite f of n plus 1 minus f of n plus f of n minus f of n minus 1, because summation is n is equal to 0 to infinite, right? N tends to infinite. So that is why we have written limit n tends to infinite f of n plus 1 minus f of n plus f of n minus f of n minus 1 plus f of n minus 1 minus f of n minus 2 plus etc f of 1 minus f of 0. So just we are expanding the summation, right? Put n is equal to 0, 1, 2, 3, 4 up to infinite. So you will get this expansion f of n plus 1 minus f of n plus f of n minus f of n minus 1 plus f of n minus 1 minus f of, because your first term f of n plus 1 minus f of n, right? Then next term f of n minus n minus 1. So first two terms, when you are comparing first two terms, first term n plus 1, second term f of n, right? F of n plus 1 minus 1, right? That is why f of n. Similarly, the next term f of n, n minus 1, f of n minus 2 minus 1, f of n minus 2, etc. Last term f of 1 minus f of 0, right? So likewise, so up to infinite, right? From 0, 1, 2, 3, etc. That is why we are taking the limit n tends to infinite. So limit n tends to infinite f of n plus 1 minus f of 0, because see, in the first bracket f of n plus 1 minus f of n, second bracket f of n minus f of n plus 1. So in the first bracket you are having minus f of n, the second bracket you are having plus f of n, so get cancelled. Similarly, second bracket you are having minus f of n minus 1, in the third bracket first f of n plus n minus 1 plus f of n minus 1 get cancelled. Similarly, etc. all the terms are cancelled. So remaining last term minus f of 0, right? Therefore, as n tends to infinite, n plus 1 becomes f of infinite minus f of 0. Therefore, limit z tends to 1, z minus 1 f of z minus f of 0 equal to limit n tends to infinite f of n minus f of 0. F of infinite can be written as limit n tends to infinite f of n minus f of 0, right? Therefore, limit n tends to infinite f of n, which is equal to limit z tends to 1, z minus 1 into f of z. Minus f of 0 minus f of 0 get cancelled, right? That's all. Thanks. We'll see you in the next video.